Okay fellows, welcome to lecture 6 of module 2 of my video series Introduction to Data Structures in C. And in this video we are going to talk about asymptotic notations. Before going to the concept of asymptotic notations, let us recall in the previous video what we had get to know. We had talked about analysis of algorithms. We had talked about some basic characteristics of algorithms, and then we had tried to analyze some small bits and pieces of code and try to basically formulate it in terms of some progression or series which we had formulated. Okay, so taking that into consideration, let us go ahead and start with asymptotic notations. So as discussed in the previous video, based on the algorithm, analyzing it gives us three scenarios. The first one is the best case, the average case, and the worst case scenario. Okay, so these are the three areas in which we need to concentrate or need to consider in order to analyze the algorithm. This is where the big O notation comes into picture. However, practically it is not required, and many a times it might not be feasible in order to have an accurate idea about the best, the average, and the worst case analysis of an algorithm. So what we try to do in terms of asymptotic analysis is to try to characterize an algorithm which is under purview in terms of another standard algorithm which we are well aware of, and try to compare whether the given algorithm is going to perform always better, or it is going to perform always worse, or on an average it is going to perform as the same as whatever is the algorithm that we know of. Okay, so the big O notation basically stands for not an accurate measurement, but a kind of a comparison of the given algorithm under purview with another algorithm with whose time complexity and its behavior is very well aware of. Okay, and in doing so, especially while considering the big O notation or worst case analysis, we tend to be very pessimistic and try to take into account the slowest possible or the most computationally expensive route of the algorithm in order to basically later on bound this performance to one of the known performance of another algorithm. Okay, so that is what we do when we consider the big O or the worst case analysis. So having talked a little bit on this, let's go ahead and see what is the big O notation. So the big O notation represents the upper bound of the runtime of an algorithm. Okay, so we say big O of g of n is equal to f of n if there exists a positive constant c and n naught such that 0 greater or equal to f of n greater or equal to c into g of n for all n greater than n naught. So basically we want to find a function g of n that is eventually always bigger than f of n. That is what this particular statement says you from n naught onwards. Okay, so as I mentioned in my previous slide, the asymptotic notations basically are a comparison of the complexity of the given algorithm with respect to the complexity of an other well-known algorithm that we are aware of. So if we can say that the given algorithm time complexity is always going to be smaller than the complexity of another algorithm, then we say that the given algorithm f of n is a subset of g of n. So that is what it means. Okay, so graphically what this is what it means. So basically we want to find a function g of n that is always bigger than f of n, okay, from n naught onwards. Okay, so mind you, when we talk of asymptotic analysis for cases where the data becomes huge and eventually we need to evaluate our algorithm or its efficiency for this huge data set, or what happens to the algorithm complexity or the efficiency of the algorithm when the data starts increasing, or for a variable set size of test size, okay, or given data size. So this is what big O stands for. Okay, so we say O g of n is equal to f of n if c into g of n is always greater than f of n from n naught onwards. Okay, so here you see this function c into g of n, where c is a constant, n naught is a constant of a particular instance of n, which is always a constant, which is a constant. Okay, so after n naught, c g of n is always bound to be greater than f of n. Then we say that c g of n, or rather g of n, is the big O of f of n. Okay, so that is what it means. Okay, so let us see some of the common big O categories and list them in terms of their efficiency with respect to time. Okay, so when we say O of 1, what we mean is, irrespective of what data you give, the time complexity is a constant. Okay, so O of 1 means to say that whatever the size of the data given, the time complexity is not going to change, so it's constant. So we say O of 1, okay, or constant k. The next, that is the slowest, or basically there is no change in the time complexity, or the slowest time complexity. The next one is O of log of n. Okay, so this complexity increases in a logarithmic way. As n increases, O log of n increases in a logarithmic way. So this is a bit faster than O of 1. Then is linear. Okay, so we say O of n, when n increases, O of n also increases linearly. Okay, so this is faster than the logarithmic increase. Then one step further, we have O n log n. Okay, so O log n increases faster than n. Okay, so then we have the polynomial complexities. So the quadratic one, O of n square, we have studied this n square in my previous video. If you would like to refer back to it, so we have a nested for loop and we get the n square complexity. Okay, so the one which is bigger than n log n is the O of n square. That is, the complexity of the algorithm increases as in terms of squares of the increase in the input data. Okay, so then we have n cube, the cubic, and in general we have the O of n raised to k, the polynomial increase. Okay, so after the polynomial comes the exponential series. Okay, where the complexity increases as a power of n to some constant, where the constant is always greater than 1. Okay, so we say O k of k raised to n, where k is greater than 1. So this the exponential complexity are higher in order than the polynomial ones. So these are some of the time complexities listed out in terms of in an ascending order. Fine. So having talked of this, we'll look into a little bit gist of what is big O and why is it significant. Suppose we have an algorithm whose complexity comes out to be phi n plus 3, then we say that the complexity of the algorithm is basically n. So we don't look into the minor details and the other constants which can be ignored. Okay, we take into account the dominant factor. Say there is another algorithm which has the time complexity of 7n plus 0.5 n square plus phi n square plus 20,000. We say the complexity of this algorithm is basically n square. And similarly for this algorithm, which has a time complexity of 300n plus 12 plus n log n, we say it has a big O of n log n. So your g of n out here is n, Here g of n out here is n square, and the g of n for this algorithm is n log n for some values of c which need to be determined. Similarly, for a negative runtime, it is not a valid thing, so we don't have complexities in negative. Okay, take that into account. Okay, having done this g of n, then we compare this g of n with the actual f of n, and we say that f of n is in the range of g of n for some value of c and n naught. Okay, so in doing so, I would like to basically give a little bit of warning, saying that do not ignore constants that are not multipliers. So be aware of it. It's not that we should always not ignore, but when you do that, be a little bit careful, especially when these multipliers have n in them. Okay, unlike here there is addition, but instead of addition, if there is a multiplier with n value involved in them, please do not ignore it. For example, we cannot say that n cube is O of n square. You can think of this as n into n square, and we cannot say that O of n square. This is false. Similarly, we cannot say that t raised to n is in the big O of 2 raised to n. Okay, we cannot say that, we cannot do it like that. Okay, because both of the terms involve n, so this is also false. Okay, so here is a little bit of a question. It is for you. Say whether this is true or false. So 4 plus 3n is in the big O of n. Is it true or false? If you say it is true, it's correct. Okay. Similarly, n plus 2 log n is in the big O of log n. Is it true or false? It is false, because we know that n increases at a greater rate, which is linear when compared to log n. So log n is not the dominant term, the n is the dominant term. So this becomes false. Similarly, log n plus 2 is in the big O of 1. Obviously it's false, because this is a constant, but it is not a dominant term. The dominant term is the logarithmic increase. Okay. And similarly, n raised to 50 is in the big O of 1.1 raised to n. Okay, so this is a series which is a polynomial, and this is, as you say, is an exponential series. This can be thought of k raised to n, where k is greater than 1, and this is, say, n raised to k, okay, where k is 50. Okay, so this is a quadratic, not a quadratic, this is an exponential series, whereas this is a polynomial series. So we know that the exponential thing is greater than the polynomial as n increases for values of k more than 1. So this is true. Okay, hope you got the concept of big O and how we analyze it. Okay, some comments on this. Okay, we say that n square plus 17 is in the big O of n square. This is true, because here n square is the dominant one. So we say this provides an upper bound for this for some value of n naught and c. Okay, n naught and c. We can also write this as O of n. So as I said, the same thing can be thought of as all these three are the same way of writing it. Okay, so the general term that is used is this, but what it actually means is this is an upper bound of this. So 3n square plus 17n exists in the big O of n square, or is a subset of O of n square. That is what it means. Okay, so that is the notation that I would write you to recommend, but however the most commonly used notation is this. We say that 3n square plus 17 is equal to big O of n square. Okay, so here equality doesn't mean that these two are equal. Since it is big O, what it actually means is this is an upper bound of this function for some value of c and n naught. Take that into account. Okay, for some value of c and n naught. So we would never say that O of n square is equal to, don't do this mistake. This should be on the other hand if you are using the equal to notation. Okay, so don't do that. Okay, let's talk about some caveats or some disadvantages or things that we need to be aware of or careful with when we especially talk of big O. Say for example, we have n raised to 1 by 10 versus log n. We know that this is the increases more slowly than this, because this is a polynomial series and this is a logarithmic series. This increases rapid than this, and 1 by n raised to 1 by 10 increases more quickly. But what is the value of n naught that one needs to take into account for this to happen? As you can see that the value of n naught for which this thing actually happens is pretty huge. So it is 5 into 10 raised to 17. So this is the point where the n raised to 1 by 10 crosses over log of n, and from there on it becomes the upper bound of log of n. So the value of n naught, even though it might exist, one needs to be very careful, and you can write it. It is not wrong to write this, but we need to be very careful at what point do this crossover actually happen, when the log n function becomes the upper bound of n raised to 1 by 10. So it might happen that this crossover might be a point where in practice it might not make sense to you. Okay, so you would rather like to stick to an algorithm which has log n complexity then basically you might stick to an algorithm which has a complexity of n raised to 1 by 10 rather than log n. Okay, because the crossover happens at a point which might actually be not a practical thing at all. So this is one of the points that you need to be aware of while choosing while considering the big O and actually using it in real life. Say for another thing is the actual size of data. Do not do big O for everything. Okay, you do big O only when the data becomes variable and these variations are huge. Okay, so say for example you need to just sort some numbers which can vary from say 10 to 30. The number of numbers can vary from 10 to 20 or say 10 to 30. In that case you have two choices, say a quick sort algorithm which gives you a big O of n log n, then an insertion sort which gives you a big O of n square. Okay, so a quick sort is expected to perform better in terms of time complexity when compared to insertion sort. But however, if your data is somewhere wandering around 20, it makes sense to go for insertion sort, because that gives you the value of n naught where this crossover happens is much beyond this range. So in reality many good sorting algorithms actually go for insertion sort when compared to quick sort when the length of data or the size of data is small, and this switchover happens from insertion sort to quick sort as the size of the data for sorting increases. So this is a classical example where you need to take care of how big O can be deceptive depending on the size of the data. Okay, so that was about big O, and very similar to big O we have big omega notation which becomes the lower bound. So here big omega of g of n of f of n, we say that is positive if there exists a constant c n n naught such that c of g of n is smaller than f of n at all time. Okay, the earlier it was this, okay, and here we have switched over. Okay, f of n becomes the upper bound for the big omega of g of n. Okay, so what it actually means is after some point n naught, this g of n is always lower than the complexity of the algorithm under purview or under consideration for some value of n naught and c, constant values. Okay, then we say that g of omega of g of n is equal to f of n. Okay, so take care of that. Okay, we say that omega g of n is equal to f of n. Okay, and similarly we have the theta notation. Okay, so we say that the algorithm under consideration f of n is theta of g of n if we can find some value of g of n such that c2 g of n is the upper bound and c1 g of n is the lower bound when compared to our algorithm f of n. So we can find another algorithm g of n whose time complexity can be upper bound as well as lower bound for the complexity of the algorithm under consideration after some value of n naught for some value of c1 and c2. Okay, then we say that g of n is equivalent to theta of f of n is theta of g of n is equivalent to f of n. Theta of g of n is equivalent to f of n. So we call that as the theta notation. Okay, so let's look into some examples so that it might give you a further clarity on the big O notation. Okay, say for f of n is equal to 4 of n and g of n is equal to n square, prove that f of n is equal to g of n. Okay, so the valid proof is to find n naught and c so that it actually happens. So when n is equal to 4, f becomes 16. Okay, and g becomes 16. So that is the crossover point. Okay, so n naught will be 4. Okay, and for c is equal to 1, this is the point where the crossover happens, and for all values of c for all values of n from after 4 for c is equal to 1, okay, g of n is upper bounded by f of n. Sorry, f of n is upper bounded by g of n. Okay, so g of n O of g of n is equivalent to f of n. Okay, so that's the proof for it. Okay, let's look into this particular loop. Okay, so determine the complexity the big O of this particular piece of code. Okay, here the loop runs n time. Okay, and it prints c n times. So obviously the time complexity is n, right? Okay, fine. Just a point to note before we go into this code, we can have infinite choices of c and n naught. It is not necessary that what is being given out here is the only one. Okay, we can have infinitely different values of c and n naught, so that this criteria of upper bound becomes possible. For another example, one could have chosen c is equal to 42. In that particular case, instead of c is equal to 42, if I had chosen instead of c is equal to 1, then n naught actually becomes 78 instead of 4. Okay, so for some value of c, we try to find out n naught. Okay, so that is how it is done. Okay, so here I have assumed c is equal to 1 and the crossover actually happened at n is equal to 4, and that was my n naught. If I had chosen c is equal to 42, then the crossover actually happens at n naught is equal to 71. Okay, so that was something that I need to tell you before we go ahead. Okay, so coming back to this, as I said, this has a time complexity of n. Okay, because it runs n time, taking into account that this takes 1 unit of time for execution. So we say that the worst case analysis of this loop is n. So we say it is bounded by big O of n. Okay, look at this piece of code. It's almost the same thing, but here instead of increment of 1, the increment actually happens. Okay, we say that for I is equal to 1 to I square smaller than n for some value of n. Okay, so in this particular case, the increase for I plus plus. Okay, so here what actually happens is basically the loop runs square root of n times. Okay, so when this condition is satisfied, I is nothing but square root of n. Okay, so this algorithm runs square root of n times. Okay, so we say that the big O of this is square root of n, and so is the omega and theta. Okay, so this is a special case, but anyhow, for the time being, take into account that this algorithm has a big O of square root of n, because this loop now doesn't run n times, it runs square root of n. And why is it? Because of this terminal condition. Okay, where I gets incremented one time, and for every increment basically the comparison basically doubles. Okay, so hope you get the idea. What about this? Okay, we have again, so this should be very, you should be very well aware of it, the square root square, right? So this runs n into n times. Okay, so we say the big O of this particular code is O of n square. Okay, so because it runs, this runs n into n times. Okay, which we had talked about in my previous video. Okay, let's move further. Look at this particular piece of code. What actually happens here? Okay, so this we are aware of, and this happens 100 times. Okay, so this printf runs 100 times, and if you are aware of my previous if you have seen through my previous video lecture, you have seen that this basically is a progression of 1 plus 2 plus 3 plus 4 up to n, and can be written as n into n plus 1. Okay, so that is what it is. So this thing runs 100 times, and these two is a linear progression where 1 2 3 4 and so on up to n. Okay, so finally the time complexity of this comes out to 100 into, okay, the complexity of this loop, which is n into n plus 1 by 2. Okay, so we say that, and the big O of this is n square. Okay, for some value of c and n naught. Okay, so the complexity of this algorithm is basically O of n square. Fine. What about this? Okay, so here what actually happens is this repeats at, this is, as you see, it is j smaller than n square, j smaller than I square, where j goes from 1 to I square. Okay, so this doesn't repeat n times, it repeats, okay, how many times? N square times. Okay, this itself repeats n square times. Okay, sorry, for j plus plus. Okay, yes, this repeats n square times. So that is what is being written out here. So this is for this 1 2 3 4 like that. Okay, sorry, this is for this 1 plus 2 4 plus 9, that is 3 square, and so on. Okay, and this loop repeats n by 2 times. So this is for that. So we multiply all these things, and this is the progression for this. Okay, so j is equal to 1t and so on. So we finally evaluate this, and the thing comes out to n by 2 bracket n plus 1 plus 2n plus 1 divided by 6. Okay, so that is the progression for this. Okay, so basically these two loops have given me this instead of that. Okay, here it was n bracket n plus 1 by 2 into 100 was for this loop. Okay, here this runs n by 2 times. Okay, and this loop, these two nested loops put together. Okay, here you see it is not linear. Here it goes linear 1 2 3 4 and so on. Here it goes square times. Okay, it goes 1 raised to 2, 2 raised to 2, 3 raised to 2. So that is what is giving you this. Okay, so here it went 1 2 3 4 like that. Okay, this one. Okay, so that is this one 1 2 3 4 and okay, so here it went 1 square 2 square 3 square like that. Okay, so hope you get the idea. So this resulted in this, as you had seen in my geometric progression, we had proved this. Okay, whereas this basically resulted in this. So that's why I said in my previous video lecture, you need to know some of these progressions and how to analyze them, so that this formulating them becomes quite easy. Okay, there are a couple of important progressions which I have given out, listed at the end of my previous video lecture. Please go through them and get to know them. Even if you cannot prove them, it's well and fine, but you should know them in order to basically formulate this kind of a progression, so that things become really easy for you. Okay, so from here on we say that it has n raised to 4 term, and rest all become which is the most dominant term. Hence we say that this algorithm has a time complexity of big O of n raised to 4. Look at these examples out here. So this again has a big O of, this is increasing at the rate of I square. Okay, it is increasing at I square, so it has a big O of log 2 of n. Okay, so this is because of the increment. So every time you are not incrementing it linearly, you are incrementing it by a square. Okay, so since the increment is by square, the time complexity decreases from n to log 2n. Okay, since it is squared, you have log 2n. Okay. Here again we have this this has a time complexity of log 2n, and this is something that we know of, and this runs n by 2 and this runs n by 2. So the time complexity O of n square log 2n. Okay, so that is what I said. If there are two terms involving n, please don't ignore one of them. Don't ignore log 2n. Okay, and just say that n square is the dominant term. Here both of them are not additive, but they are multiplicative. So take both of them into consideration when you write big O of n. That is what I meant a couple of minutes ago. Okay, and the complexity, this loop runs n by 2 times, this loop runs log 2n times, and this loop runs log 2n times. So the the total time complexity of this particular algorithm or code would be O of n into log 2 of n into log 2 of n. Okay, so that was about it. Okay, so before I end my lecture, let's look at a couple of brain teasers. Okay, so for given these three statements, which of these three is true? Okay, that is n raised to k is in the big O of c of n. Okay, or n raised to k is the omega of c of n, or n raised to k is the theta of c of n. Okay, so obviously this is what we say, a geometric series. This is a geometric series and this is an exponential series. Okay, so this is obviously greater than this, so it has to be big O. Okay, so this was the exponential series and this is a geometric series. When I say geometric series, what I meant was a polynomial series. Okay, so this was a polynomial series and this was a exponential series. Okay, so obviously exponential series is bigger than the polynomial series for some value of c and n naught. Okay, so this is true. Here I would like to basically categorize you, ask you to categorize whether this function is a constant, linear, is it increasing polynomial, or is it increasing exponential. This, as you can see, is a polynomial, this is a constant, this is linear, this is again a polynomial, this is again 2 raised to n, so it is again a polynomial. Okay, sorry, this is an exponential. Okay, so this is exponential, this is a polynomial again. Okay, so this is linear and this is linear. Okay, so that's it. Okay, just go through it. So this is a constant, sorry, this is constant and this is linear. So just to make things much more clearer to you. So then I would like you to basically arrange them in ascending order. Okay, so the slowest to the fastest. So obviously this is the first one, and then what comes next? Okay, this one, then this one, and then so on. Okay, so as I said, these three, and then n cube, and then 3 raised to n, then 2 raised to n. So that is how the complexities increase from lower to higher. Okay, so similarly for this, we have this one and then so on. So go in this range. First comes the constants, then come the logarithmic, then comes the linear, then comes the linear arithmetic functions, and then comes the polynomial functions, and then comes the exponential comes in. Okay, so keep this in mind. This is how the series show a greater change or greater increase as n becomes more. Okay, so arrange the given functions in terms of this, and that would basically give you a result. Okay, as I said, this is a constant, then comes the logarithmic. Okay, log 8 raised to n, and then obviously log 2 raised to n, which increases faster. Then obviously there is a linear n into log n, so that is a linear arithmetic or a linear logarithmic function. Okay, and then 4 of n, which is a linear function, and then n square, n cube, and then finally the exponential one. Okay, so okay, the last one, match the equivalent. So tell us which is the big O of which. Okay, so here obviously this becomes the big O of this because n square, so n square plus 2 of n, both of them have a big O of n square. Okay, so both of them have a big O of n square. Okay, so in this particular case obviously it is this one. Okay, so both of them have a big O of n raised to 4. Okay, and then finally we have this and this. Okay, sorry, this one. Okay, so both of them have a big O of n, and finally this is equivalent to this because both of them have a big O of log 2 of x. Okay, so hope you have enjoyed this video lecture, and the concept of big O was made pretty clear to you. If you still have doubts, you can go through my lecture notes and the PPTs, and you can post questions to me at any given point of time. Thank you, and stay tuned with me for my next video lecture.